Has anyone ever read The Republic by Plato? Yeah. And it's called The Allegory of the Cave. But, in this picture, I think these are you guys. You're the students, and you're chained here to your seats there. And here we are, the professors, and we're saying this is reality. We're putting puppets there and say, oh, there's a horse and there's a dog, and there's our slides that we're showing you, and we're saying that's the reality, So, but actually, reality's out here in the bright sunlight, the real world, which is even too bright for us. We have no idea what's going out there. It's just too bright. Reality is just way too complex. So we try to simplify it with models, right? But I think if you ever hear of an academic who says, I have the true model, right? And, when they teach econometrics, I think it's the biggest BS when they talk about consistency, and there's the, consistent estimator of the true parameters, right? Basically, I like this saying, this guy is George Box, and his saying is, all models are wrong, but some are useful, right? So that's the reality. All our models are wrong. By definition, they're a model, they're not reality. And at best, you should think of econometrics as approximation theory, right? And that's how von Neumann, he's one of the people I really admire. I mean, he's really changed. If you think about anybody who's changed the world, he is the inventor of the digital computer, really, essentially the von Neumann machine. And he also invented game theory, right? Von Neumann and Morgenstern, expected utility theory, right? He's a math, and you could almost say he's a polymath, but he says truth is much too complicated to allow for anything but approximation. So I think that's what you should think about our models. Maybe our models are getting more and more better approximation. That's what we're trying to do, and get them as good enough as we can to the point where it really helps us in thinking about the world and understanding what's going on. But when thinking about auctions, I think auctions, I really was jazzed about this ability to work with Harry on auctions, because I just think auctions are really cool just in themselves. But there's this whole literature on market design. And if you think about the Nobel Prizes in this area, Roger Myerson, Paul Milgram, I have two colleagues. I used to be at University of Maryland, Larry Ausubel and Peter Crampton. And along with Milgram and everything, they're designing these FCC auctions, right, for cell phone. And they had something called a reverse spectrum auction, where the TV stations had been given a whole bunch of frequency bands. And they just realized, like, most people are using cable TV. So they wanted to kind of sell those, get the TVs to give it back, the TV stations, and then retask it for cell phone. And so they had a kind of a double auction of TV stations selling off their bands, and then cell company buying it back. And it's incredibly, and these guys designed this thing called a simultaneous ascending bid package auction. So you could buy frequency bands in different parts of the country, and they wanted complementaries, like maybe AT&T or Verizon want to buy in all the major markets and kind of get a foothold there. So they're buying bundles of frequencies at different frequency bands. They may want to have it's really, really complicated. So all I want to say is they designed this auction. It's unbelievably complicated. And I don't even think they would say they have any idea how to solve that auction or bid in that auction. It's so complicated that I think they were just thrilled when the auction went by and people actually, these big companies could actually bid in these auctions the first time, right? I remember Paul Milgram come to Yale after the first auction, and he declared it a success. And I think somebody might have been Ariel say, well, how do you know it was a success? He said, well, it raised billions of dollars, right? So I guess but there's no benchmark to know how you evaluate that. So maybe the criticism for me, and I really admire these guys are really doing big things. I mean, this is, and it's not just auctions and raising a lot of money. There's the kidney exchanges that are helping people save lives, right? And Al Roth, another Nobel Prize winner, doing that. So it's you don't want to be a market for kidneys kind of ethically indefensible. So you have an exchange, and you want an efficient exchange of kidneys, and they have to be matching. And Harry has worked on that as well, and with some doctors, and that's very, very cool stuff. So I think this is an example where economics is really making a difference, and so that's where we can say, wow, as economists, we can really have value added. Now, as a structural econometrician, we're and modelers, we're kind of lagging behind, working on little problems. Well, why do I work on little problems like bus engine replacement? Well, partly you're developing methods that might be more generally applicable. But we do want to understand things, and that's why I'm not a macro. That blows me away, right? Macro is just too many things going on, and you have to cut a lot of corners. So they talk about heroic models, and I don't know if they call. I almost consider that, John, you have a heroic model. It's almost kind of like an insult, right? It's the model is like trying to do too much, and it's sloppy. So I don't want to be. There's different ways of doing science, and I'm just saying this is the way I do science. So. I'm going to go back to the little auction that we're talking about, Korea. You say, like, who cares about bus engines, and who cares about wholesale auctions of rental cars in Korea? But, we have really great data for this. And it's a simple enough auction that we think we can make progress. And Harry's work has made progress, and we're thinking we're making progress on modeling the dynamics of auctions. And maybe through a number of steps, 10 years from now, we'll actually understand how these FCC auctions work, and maybe even find better ways of doing this than the ones Larry Ossabel and Paul Milgram have designed. We don't know. So why don't we just play an auction? So how many of you were here? I presented this at the conference yesterday. So most of you saw it, so the thing. So I want to play an auction with you. So I have it right here. Let's see if I can you see the screen? Yeah, let me see if I can increase the font size. Huh? You can do that, yeah. Okay, all right, good. Okay, now, here's how it works. So remember, it's a 2-minute auction, but we're going to do it is if I actually ran this in 2 minutes, I couldn't. It would just run by you. So we have some robot bidders you're playing against, and just like this auction, we don't know how many other bidders are in this auction. It's just like a real auction. It's just that we're playing against robots. And I'm starting you out that you think this car is worth $282. No, we think we're going to try to bid collectively, and see what you think to bid. It's $8,200. We think we could sell this car. If we can buy it for less than $8,200, then we can sell it at our car dealership to some unsuspecting consumer. Okay, this Avante, right? XD 1.6 liter. Okay, so I'm going to we want to buy it for less than $8,200. We're going to have 121 opportunities now, but we're slowing things down. We're going to say, second 0, we're waiting for the first bid, and then we'll get to talk a little bit. But I'm working now on a version that you'll play it in real time. And let me tell you, it's a lot harder, right? Because you really only have 2 minutes, and it just takes a little while to type your bids. So we're starting the auction off, and it's second equals 0. So what should we do? We could just hit return and pass, or should we make a bid right away? Does anyone say make a bid? Who's up for making? So let's just hit return. Okay. And then it says your highest bid is so far as 0. Enter another bid. Let me see, it's going off the screen a little bit. Let me see if I can stretch out a little more screen here. So, okay. Maybe I should minus it, make it a little bit smaller. How do I do that? Just, Command minus. Okay. Okay, see if that works. Okay. Is this one? Enter full screen. Okay. Okay, so I'm going to just pass for a little bit. 8,200. You're not the high bidder. So it means somebody already made a bid, because just telling me that I'm not the high bidder, there's got to be a bid. So let's just see if they start a little. How about if we just for the heck of it, let's put 200 in there, and let's see what happens. Oh, now we know it's already. We're learning something. The high bid is higher than 200. Okay, so somehow in the first couple seconds, someone's come on the table with a higher bid than 200. Now, should we try to learn faster? You know, we can go all the way to 120, so we could let some time go by. It doesn't hurt. And maybe, you know, we talked about irrational overbidding, so we don't want to push it up too high. So trying to learn might actually force the other guys up. So maybe you let some time go by. Hey, it's 18 seconds just for the heck of it. How about if we go to 1,000? How many people think if I put 1,000 now will be the high bid? Now, by the way, how would you know, right? How would you know? I mean, yeah. Yes, you saw some data. Yeah, these are estimated robots. They're like the human stand-ins with their parameters. So you saw some auctions, and you said before the average price was 5,400 or 5,800. Right, so that gives you some prior, but it's a little bit like Nick's talking about ambiguity. This is ambiguity, right? You have no idea what the distribution of bidders are. You know, you saw something about my paper, but you got a very fuzzy notion of what it is, and you kind of know that 5,800 is the average price in the auction, but they could go to 10,000. They could be as high as low as 4,000 or something. Okay. No, we don't know how many robots. There could be none, by the way. We could be bidding, well, no, we do know, yeah, we know that because somebody there is, because yes, if you're the high bidder all the time, we wouldn't know, but now we know there's at least one other bidder. That's what we can say. Yeah, absolutely. So let's go to I bid 200. Let's go to 1,000. Let's just be crazy, right? Now we'll find out if that's a smart thing or not. Wow, we're not 1,000 now. So what do we do? Should we let more time go by? Yes. Okay, we'll just click by. We'll let some time go by because we got plenty of time, right? You know, what's the rush? Yeah, yeah, we're just looking out the window. You look at your cell phone for a little while. Yeah, and we'll go on. Well, now let's go about halfway through the auction, 60 seconds. So anyone want to suggest a bid that we should go now and try see where the auction is now? Can I keep bidding? Can you keep bidding 1,000? Well, if we bid 1,000, we won't do anything, right? Because we're already at 1,000. We have to go higher, otherwise we're just repeating it. We have to improve our bid or not bid. Yeah, we could bid 1,000 again. The robot only knows the other robots only know whether they are the high bid or not. So one of the robots knows they're the high bidder, but all the other robots know the same as us, that we're just the high. They know whatever their bid is, and we don't know what it is, and they know that they're not the high bidder. So they're just like us. We know our high bid is 1,000, our value is 8,200, and we know we're not the high bidder. And there's a bunch of other robots that know that same thing, and then one of the robots knows they're the high bidder. 4,100? 4,100. I'm going to go 4,100. Now it's recorded, Harry, and you're the auction expert, so we're going to hold it to you. All right. And that wasn't good enough. Whoa. So what do we do? Should we pass for a little while? 41. You know, we still, you know, we're about halfway to our, you know, we may be greedy if we think we're going to get a lot of, you know, if you're saying 5,800 and we should expect about 3,000, maybe you're too greedy. Maybe this is an auction where a bunch of bidders entered who have really high valuations for the car. So maybe, you know, 8,200 is, you know, we can't expect to get this auction to be that low, or, you know, 5,800. But let's go up to 90 seconds. So we're just going to pass and smoke a cigarette. All right, and now it's 90 seconds in the auction. So what should we do now? We're paying attention again. What should we do? Huh? Bid creep. Okay, so let's go to 4,600. Not the high bidder. Okay, let's jump. I'm going to jump. I'm going to do a little bit bid jumping. How about 5,400? I'll take responsibility for that one. Not the high bidder. Whoa, it's gone up. This is going to be an expensive car. Okay, so what do we do now? 6,000. Do I hear 6,500? Do I hear six? Going, gone. 6,000. You said 6,000? Okay, you're going to have to pay for this, Harry. And you're not the high bidder. Well, should we go like what's called straightforward bidding? Just keep going up, and then we're gonna have to drop out when we hit our valuation. Should we jump higher, or should we wait for a little bit? So how high should we go? Should we go up to 7,000? How many people think we should go to 7,000? Yeah, we still get 1,200 a profit, right? Now, should we go now, or should we wait a little bit? Okay, 7,000. Oh, hey, we did it. Now you have to wonder, we're the high bidder. Did we go too soon, too fast, right? You know, now you say, okay, you know, on the one hand, you won, but then you're wondering, man, maybe we should have creeped up to this. Like Aaron was saying, we should have creeped. So we might, you know, at the end, we're going to compare ourselves to an optimal robot, and we'll see, you know, if that is too aggressive. So what now? How many people think we should hold for a while? Let's see how long we stay the high bidder, right? Remember that graph I showed you. Once you're the high bidder, you should expect to stay the high bidder for at least a few seconds. So let's just test that. Oh wow! Now that theory didn't work here. So we got outbid right the next second. So we're at 95 seconds. So we're going to go to 120 seconds. We have 25 seconds left. Should we just stay there at 7,000? Anyone say we should jump in now, go fire? Okay. Okay. So how many people think we should go up to, let's say 7,500? Well, Harry, you're the auction expert. What should we go now to?
N minus 1 over N, so point over just one bid, I bid half, and then 2/3, 3/4, 4/5.
Okay.
So we're up to 4/5.
Okay.
There's more than 7. They're almost going to get very close to the bid.
Okay. Valuation. Okay. How many people think we go, you know, follow the auction expert and go 7,500? All right. We're not gonna argue with Harry. We're going to go 7,500, and you are the high bidder. Okay, so we're now the high bidder. Now let's test it again. We're getting down 96 seconds. We're still the high bidder. Okay, so there we go. We're still the high bidder. Maybe that's gonna work for us. Still a high bidder. Oh, now 100. Somebody bid us. You know, we're no longer the high bidder. So now we have $700 of gap, right? A potential profit. So our potential profit's going down. So the question is, you know, we don't want to stop now, right? We're probably willing to go up higher, right? So the question is, how much higher do we go? So we have 100 seconds. How many people say we should just wait for a few more seconds? Okay, let's wait. Let's just go a few more seconds. Let's go to 110. Okay, now we got to be careful. This is now we have to talk turkey. What are we going to do? 7,500. Should we? Anyone think we should go to 7,700? 7,700. Would that? You want to try 7,700? Yeah, let's try 7,700. Okay. No. Okay. I'd say 7,900. Go up. Go 7,900. All right, let's go to 7,900. Not the high bidder. Oh, I don't know. I think I'm worried we're going to lose this auction. Let's go to 8,000. How many? Does anyone think that's a mistake? 8,000. We have $200 left of profit. Not the high bidder. And we're 113 seconds. Don't go any. Okay, now it's 119. We got two more opportunities. We had 119 and 120. So how many people think we should go? You know, I mean, if we could just lose right now, we get zero. But you know, we could 8,100 and still walk away with $100, right? You know, I'm not going to say no to $100, right? So, what do you think, Carrie? 8,100? Okay, let's just try it. Not the high bidder. So one more chance. So how high should we go? Yeah. 8,199. Just to say we won, right? You know. Sorry, somebody bid. Now let's just take a look at, we lost this auction. So let's just see, this is the outcome of the auction. And we're the last person here. It's too small for you to see, but there's our value, 8,200. There is a bidder here who valued this thing for $10,000. $10,000. But who was the winner? It's not the highest. It was winning bid. Oh, it was by 10. So here we have what's called ex post efficiency. The highest bidder is B10, and B10 beat us out, and they bid 89.57, and they did that at 117 seconds in the auction. So just a few seconds, they beat us out, and we lost. Okay. So that's an example of an auction, right? That's exactly how the Korean auction was, except you have to do a lot faster and think in 2 minutes because you're in real time. And we'll have a real-time version of this out. But let's now just do one more thing. And let's just look at the optimal bid. So we have a robot. We calculated a robot, which we talk with no bidding frictions. And what would the robot have done if they were to bid at exactly the times we had bid? So the first bid, the robot should have said it was optimal bid essentially 0. We bid 200. So there already we have early overbidding at 4 seconds. We're 200 over what the robot would have done. Now, where would the robot ended up? The robot would have ended up at 81.42. And so we're much closer, and that's what we saw in the data. We're at 81.99. We were willing to just kind of almost exhaust all our surplus. The robot would have held in the highest after all these bids. So you can see at every point, we are higher than when the robot, right? And it starts to the gap starts to catch up here at 92 seconds. We're bidding 6,000. The robot would have bid 5,400. Here 7,000, 6,000. So we're starting to catch up by one. So this is what we call the deviation path. We made this deviation, and then the robot says, "Okay, hey, wow, you bid higher than I thought. But given that I'm here, that's dynamic programming. What's optimal going forward?" And what's happening is these gaps are lowering. So by at 112 seconds. The robot would have bid 70. We're only 100 over, and then by 119, we're only 48 over, and by this 81.99, we're about a little bit less than 47 over. Yeah, Harry.
Is it just a freak that the actual bid becomes the predicted optimal?
Oh, that yeah. So. Here it's like holding, if your actual bid was 77, it just says don't increase it the next time, right? So there's a long time where it's here it's really like the robot saying don't increase it any further. Okay, so just bid 7,700 again. That's what you should do, right? Okay, so there's the game, and we actually, the robot, we lost and the robot would have lost. But when you play an auction, that's the trade-off, right? You want to, you don't want to just maximize your probability of winning, because if you overbid, it's the profit conditional on winning times the probability of winning, and you're trying to trade those two off against each other. So I'm going to go, instead of going through all my slides, I'm going to spend some time on what I didn't have time to go through yesterday, and to convince you of some counterfactuals with these robots, right? The robots seem reasonably smart when you play against them, and they are intelligent. We used our econometrics, our dynamic program to build these traders, and we want to say, how well do we do against the computer? Now, we know in many games, and von Neumann, the idea of minimax theorem, right? And that's a kind of elementary kind of Nash equilibrium. And what we know is, a lot of us in economics want to hang on the idea of rationality, that humans are perfectly rational. And I think that's just like, I would call it physics envy, right? We want to have because Nash equilibrium is really cool and you can develop these really complicated theories. But we know already that humans are not perfectly rational. And what's exhibit A for that is the fact that AlphaZero, that's the Google chess program. You know how AlphaZero works? Does anyone know how AlphaZero works? It's a deep neural net that uses reinforcement learning, the same kind of dynamic programming we've been teaching you, but with a very flexible approximation architect using deep neural nets. And they played AlphaZero against each other for just 24 hours at Google on 5,000 tensor product units. They're kind of like GPUs. And within 24 hours from zero, they just initialized, and these programs would play against each other. They bootstrapped and became superhuman. They're better than Stockfish, these other programs, and they're way better than Magnus Carlsen. I mean, just blow them out of the water. So you basically have, now we don't know, have they achieved the perfect minimax equilibrium of chess? That's not known yet, but already they're better than any human on Earth. And this has been the case since 1997, when there was IBM won a tournament called the Deep Blue, right? So if the computers are always winning against us, that we can't be playing Nash equilibrium. We can't be playing minimax, right? We're doing something less than that, right? And I think over time, we're going to find more and more. This is what Herb Simon called bounded rationality. So, that's not to take away that we're really smart, but we are not designed. Evolution didn't design us to play chess, right? Evolution designed us for a lot to adapt. And so we're really, really smart in doing a lot of things, but we can't do one task well. So it's not surprising if you focus all of technology on solving one problem, that computers will beat us. But the question is, the scary thing going forward is, wow, when does this computer start getting better and better and so many other things, right? And what is left for us to do, right? Like apparently reading mammograms, you can have machine learning algorithms find tumors in mammograms way better than humans. Humans miss potential tumors, and they can scan and detect tumors better, and they've been trained to do things like protein folding, three-dimensional shapes of protein folding. It's called AlphaFold. Now they have predicted three-dimensional structures of molecules with the same kind of deep learning architectures, and Google is doing that. So it's really almost a little bit scary in some sense, right? So let's I'm going to not going to go too long. We'll kind of let you go early. I'm going to switch back now. How do I get out of? How do I get out of the screen here? Oh, there we go. I don't want to do that. Why am I so dumb with this? Okay, here we go. All right. So now let's just go to the slides again. And let me talk about these counterfactual, because it goes back to comparing humans versus computers. And there's von Neumann. So we kind of showed that if you try to solve a perfect Bayesian equilibrium, that can't explain early bidding. And we introduced this model, a 4-parameter model of rational intention using dynamic programming. So where rationality comes in is that we use the data to estimate this distribution of the high bid. And that's where, we're just using a lot of data. And you might say humans playing this, they just don't have all the data that we have. We see all these auctions, and we're just assuming somehow that humans are smart enough that playing a lot of auctions, they're going to essentially learn this, but we're not we haven't provided a constructive way that they would actually learn it. So Bayesian learning is a one way, but it's too complicated for us to do. But you might say, you could imagine a econometric estimator where using data, you could run this econometric estimator and get an estimate of this. Here we're pooling all the data, but with samples, so there's a sampling bias, right? You only see the bids, a selected number of high bids at the time you're the high bidder, and that's kind of an endogenous sampling problem. But we know how to solve these things. And it's like a Heckman selectivity bias. We have a paper in Journal of Econometrics last year. It's a little bit like Andrew was talking about. If you see, look at a steel company and they buy steel at wholesale prices and they sell it to retail customers like other firms at a markup, at a very small markup. So they're buying lots of steel and then selling it. But what we see in the data is only when they buy steel. We don't see on the days they don't buy. So steel goes up, it's like a really competitive market, and it's got an AR1 process. The price is going up and down. And what you see is they're trying to buy low and sell high. So they buy more, just like a consumer would, right? Buying in their inventory makes a difference. We have what's called an SS strategy, but the SS are a function of the wholesale price. But we only see the prices on the days they buy because they don't bother to write down what the prices are on the days they didn't buy. And you might say, like, well, and how do you estimate an AR1 process if you have that kind of sample selection? And we show you can. We can show you can correct, and using a method of simulated moments estimator, we can uncover the true AR1 process. So although we haven't done this, we kind of assert something like that could be used to uncover these beliefs. So we have a non-Bayesian learning where experienced bidders would somehow learn this, but we haven't explicitly shown you how we get to that. And then once you get that, we talked about it. These are some of the sample paths and representing the mean beliefs. This is the mean high bid, and as the auction goes up, and then once you're the high bid, it can jump down because empirically in the data, if you're the high bid at a certain second, the next few seconds, you'll probably be the high bidders until someone jumps ahead of you. Okay, now we estimate this model. And let me just go through something I didn't have. I talked a little bit about the dynamic programming. So let me show you this last period here. So this would be at second 120, and you come into it that second, with a bid that, like in our case, we had some high bid that we had, and we were were we the high bidder right at 120? We were not, so that would be a 0, and then we would know our highest bid up to that point. And we'd have a belief about if I submit a bid of B above BT, what's the likelihood that we would win the auction? We'd win the auction. It's the last chance. And then we're saying the probability that I win times the profit conditional on winning, right? So that was 8,200, and then we bid up 81.99. So we didn't win the auction in this case, but if we would have won, we only would have made $1, right? We would have bid away all our surplus. Okay, and now what you do is you do backward induction at time t. We assume there's an extreme value shock, which is a bidding friction that Bob Miller also did, and Aaron have in your paper. But well, you don't have extreme value shocks, but you have other kinds of frictions. And this says either if I draw a big enough shock, I just don't bid in the last period, or I pay a cost to calculate and I try to maximize. And this little WT is now a conditional value function, right? A choice specific. This is the state, and this is now the decision, but the decision happens to be continuous. And we calculate that by dynamic programming. And now here's the equation here for time t-1. This is a choice specific value function. So if I'm at 119 seconds, and here's where you see the rational inattention. This is saying if I bid B, so I'm coming in at 119 seconds with this bid so far. That's the highest bid I bid right at 119 before I've submitted my bid. And I either know 0 or 1, I'm the high bidder. I bid this amount. Now, if I bid this amount, then next period at, this is the probability that among all the people who bid at 119, I will be the high bidder. Now, if I'm the high bidder, then next period, this becomes a 1. See, there's a 1 here because that's saying I won the high bid contest. And now at 120, I'm the high bid going into the very last instant. But with 1 minus this probability, I'm not the high bidder. So then I get a 0. Someone beat me. So this is the value if I am not the high bidder at the last second. And this is the value if I am the high bidder at the last second. And then what's this? This is the probability I'm inattentive. Now, if I'm inattentive, I'm not going to improve my bid anymore. I'm just tuned out at the last second. I'm the high bidder. I bid B, but I just submit the same B because I didn't even bother to bid. So it's like submitting the same bid. It's like not bidding. Now, with 1 minus P, I could be attentive. And if I do that, then I get the max. And I can either, now I'm actually thinking, but I'm thinking, do I want to calculate the bid or do I just want to stay and bid B? I could do I get the max of the expected max. And that's what I showed you up here. And that expected max is, oops. That expected max is this, the thing you've been seeing here, the log sum, right? Okay, so that's just how, and then we keep working backwards. This is kind of generic. At every time t, it looks like this, and it's accounting for the chance that's where it's rational. I have a probability, and I know that I could be tuned out, and I want to account for that probability of being tuned out in the future. So it's inattention and rational because I build it in when I do my backward induction. Okay, any questions there? Now, I'm just want to, first of all, show you how we can do a counterfactual without even actually estimating the model. This is where we use a little theory. What happens if we remove this informational restriction that you can only see your own bid and only just this 0-1 indicator? So suppose you could see the high bid. So you're going to keep it all anonymous. You won't see anybody's identities, but just for free, you always will see the high bid at every moment in the auction. Now, intuitively, what do you think that's going to do to your bidding strategy? So now you at least see the high bid in the auction every second. What would you do when you knew, what would you think you would do on that? Would you bid more aggressively or less aggressively, earlier or later? Does anyone have any intuition? Huh? Not bid. There you go. Yes. You're going to be an informational free rider. Why should you get out there? What's the gain? You're not learning anything. So you have no incentive to bid. You know, when there's the information restriction, you want to bid to learn. But now you get the information for free. And what's going to happen? If I bid, I might just only push the bid higher. So I should just sit there and wait in the background and wait till the last instant in the auction, right? Is there any reason I should bid earlier? No. So, you know, it's almost like common sense that we can prove this, but we need a couple of assumption. One is called stochastic monotonicity. And what this equates is right here. It's saying if I enter a period with a higher bid than a lower bid, so now this distribution, first of all, the H indicator doesn't matter anymore. Because this is now not my own bid, it's the highest bid in the auction. I'm just getting that for free. That's the highest bid of any bidder in the auction. I observe that every period. And then this is my belief about in the next instant, what will be the highest bid. It's like a Markov process, right? A conditional probability. And now it's saying if I enter any period with a higher bid than another bid, this distribution is going to be stochastically dominant. In other words, it's saying if the bid, because it's ascending bid, whenever the bid is higher, I'm expecting the bids to be higher as well. So that's called first order stochastic dominance. Now, if we make that assumption, we can prove this theorem. We have to assume the bidding frictions are zero, but we can have irrational inattention. We can do this by just a mathematical induction proof, backward induction, but the proof is by backward. I won't go into the details, but the intuition is exactly, you don't bid at all until the very last period. Very strong prediction here in this model. But the prediction is very intuitive, right? Nothing to gain from bidding early. Okay. Now, you bid at the very last instant. You just wait till the very last instant, and at that instant, you're bidding like it's a static seal bid auction. You have a prior about how many bidders will enter in the very last. Everyone will enter and then just bid as if it was a static auction, well, single period auction. And that, Harry has a really nice, the Poisson assumption is a beautiful formula for that optimal bid if you assume a independent private values, but McAfee and Macmillan they have worked out the general case of prove the existence of an equilibrium where you have a prior over the number of bidders and it's a one-shot auction. No, you're going to shade your bid because it's a first price auction. There'll be a bid function and you will shade your bid. And Harry has his really beautiful lecture notes. They worked this out in the Poisson case, and it's a really cool formula. Very, very intuitive, nice formula. Now, let's. I'll say just a little bit about maximum likelihood because we actually use something called quasi-maximum likelihood, but intuitively, maximum likelihood is just this. You see a single bidder. We're going to focus on a single bidder in a single auction, and we have these 4 parameters. So that's tau. It's V, C, P, and sigma. And the likelihood is that every second they might bid 0, they might bid a positive amount. We see, in the case of the informationally restricted auction, we see that whether they're high bidder or not, we see their previous high bid, and then they see the amount of a new bid, and then we maximize that. Now, in the full likelihood, we can discretize the bids to the nearest, and they're all in just to the nearest integer in the data. So we could actually literally just do a logit. So here, it's the maximum. There's a shock for every possible bid, and then we get this just standard multinomial logit, except there's a large number of bids here. So there's this sum is, if my current bid is 3,000, I have to sum for every B prime, from 3,000 to 10,000, right? And so that just gets very tedious. You're like exhaustively searching over the grid of all bids to every nearest integer and evaluating that. Now, that just turned out to be slow, and we try to work on ways to approximate this sum more efficiently. But what we actually do is the quasi-maximum likelihood. We just do a continuous maximization and round it. So here we use the MATLAB fmin bound functions, one-dimensional search, and it does maybe 15 or 20 search. It uses a cubic approximation to the value function. So we approximate the value function using interpolation over a grid, and then fmin bound just takes this, and within 15 or 20 guesses, it just nails it to 3 or 4 decimal points to the optimal bid. So we're just doing that repeatedly in doing this backward induction. So, and then here's how we get the likelihood. Now, here's what we do to show you the likelihood. Let me show you this. We have these same kind of transition probabilities, except that if you improve your bid, this is the probability of not bidding or making an improved bid. But then this last term here is because this is what's called a statistically degenerate model. Okay, this thing here. See, MATLAB calculates an optimal B prime. Or no, this is the thing coming out of MATLAB. MATLAB's calculated the optimal bid for every B and H. It's the predicted, but there's no room for error, right? It's either you bid exactly or you have zero likelihood of observing this, right? So, we have a zero likelihood problem. If we tried to do this by maximum likelihood, and almost all the time, the actual bid in the data, B prime, will not equal what comes out from MATLAB. So we have zero likelihood. Now, what do? We say, well, I'm going to give this a probability. This is I have the value function of making this potentially suboptimal bid. That's generally going to be less than this. This is the highest value because you're bidding optimally. So this is some suboptimal. So we're going to weight this like a binary logit. And it's saying the more suboptimal you are, the less likely you're going to bid. The highest likelihood is when this equals this, that gives us a probability of 1/2, right? So this is this is a model where it's gonna be nice and smooth in the parameters. The maximum likelihood is going to be like a calibration procedure. To maximize the quasi likelihood, you want to try to make this to be as close to this as possible to fit the data. Okay. That's the only innovation that we have here. And so here's what I was showing you yesterday, that you can see how it's trying to fit. These are a bunch of data points. So it's kind of like a nonlinear regression, right? So the model is predicting for these so for this guy, the value is predicted to be 6511, just 1 unit more than their actual bid. They have a 99% chance of being inattentive, a cost of minus 2.85 in sigma. These are the maximum likelihood estimates that come from the quasi maximum likelihood estimates for this bidder in this auction. Okay, so it's like, you can think of these like fixed effects estimator. All right. Now, what's happening here is, this thing could kind of predict lots of different paths. And remember, we talked about these 3 different paths. The blue dots are if the bidder never bids at all, and the first time you enter it in the auction, if you haven't entered so far, you first bid a little bit over 3,000, and then around 50 cents, you jump up to this next plane, and then you start jumping up toward the end. And if you sniped, the optimal model is if you first enter here, you'd want to bid up there. Okay, the optimal snipe bid is up there. Now the next bid is if I was to constrain myself to bid optimally, but at the times the human actually bid. And we showed you that, I showed you that calculation after we played the auction just now. The green line would represent the amount of the actual bids. And see, the first one, the green says, I should only be bidding down here. And then this human bid above, just like we did. We bid early overbidding, bid too much relative to the model. And, the dynamic program said, hey, that's dumb. Why'd you do that? But then it can recover. So once you bid up there, the black line says, okay, I'm off the equilibrium path. But given that, what's optimal, so dynamic programming is always looking forward, saying no matter how you got here, always do the best you can from where you are, right? So now it's just kind of randomly just perturbed you. And now it's actually from there on, the dynamic programming fits you pretty well. So in other words, the quasi-maximum likelihood is decided, let's take the big hit here. There's a big hit here where there's a suboptimally, but then we only have one. Now it could have pushed this whole path up, and then it might have nailed this first one, but then it would overpredict the other ones, right? So it decided that to maximize the likelihood, we just want to have one overprediction that's early, and then the rest I can follow that path. And those deviations, the model's fitting really, really well. So that means that's why the model fits really well by the final bid, because it's doing much better. It's just higher. It's just better for the likelihood to fit all of them this way than to try to fit the first bid. Okay, so that gives you a sense why the model's getting the over early bidding. That's given our quasi likelihood. That's is the best way to fit the data. We just, you might say, well, can't we have any more flexibility? Can't we have this thing go up like this. And, you know, well, with our 4-parameter, we just don't have the flexibility to kind of have a path that goes like this. It goes all through the day. We'd love it if we did, but, you know, we searched pretty hard and this is the best we can do. Now, I want to convince you, and in the last couple minutes I have, that, you know, first of all, what snipers we can match, right? Because, you know, we showed you one sniper yesterday because there's only one bid. So for the snipers, we can get it because we're just adjusting the value that we can get a path that only goes through one. We're only fitting essentially one point, and so we can nail those most of the time. And that's why when we compare predicted versus actual sniping bids, we're doing, you know, really nicely. Now, if we look at everyone else, the final bids in the auction, these are all 533 auctions. The winning bid, we're pretty close to the line, but as we said yesterday, the errors are not symmetric. It's not like a regression where you would see some, you know, mean zero errors, right? We're seeing prediction errors that are in the upward direction, and those are those early overbidding that most of the time. And then if we look at the first bids, it's terrible, right? We have some on the line here. There's some people we can nail there, but most of the, you know, and here we have 4,029 because we have in these 533 auctions, the average number of bidders is like 8. So we get 4,029 estimations that we did. And in most of these cases, the model's under predicting the first bid, but the final bid, it's getting it good. So now let's just, I want to convince you that, and here's another picture of the early overbidding. So this is the data. This is the mean high bid over all these 533 auctions. And then there's quantiles like the median, the 90th, and it's like a 95th percent confidence interval around this mean bid. And this is our model. If we simulate our model over these 533 auctions, what we see is the model predicts a little bit higher than the data, but then in this period, it's way below. So there's just a lot of overbidding here, but in the end, they catch up and they're much closer. But, you know, what we'd like to see is these two curves lying, you know, if they are lying on top of each other, I'd be saying, hey, I've nailed it. We've nailed it with this model, right? But this is a sign the model doesn't fit the data. Okay, so I'm being admitting we have a ways to go. We have to explain what they're doing. We're not doing it yet with this model. Now, but what we're going to give an explanation, we're going to say that these guys are not rational. They're not fully rational. We're going to say our robots are better. Now, remember what we did in the auction, the ones I was showing you, we can look at the times people actually bid and say, what should they have bid? And now what we can do is go through all these 4,029 bidder auction pairs, and in each auction, we can deviate one player. So we'd say, in each auction, I have my robot bidding for me. So I'm going to hand over the bidding. I'm going to tell the robot, I want to bid now. But instead of me typing it in, the robot's going to say, John, you should bid 4,029 or 4,057. And I'll type that number in. So if I follow my robot's advice, it's like a deviation strategy, but otherwise we let all the other bidders, their bids are unchanged unless I become the high bidder, then that will change the auction price. So let's see what happens when we do this. So what we see is these are individual bidders. This bidder one was bid in 163 auction. Here's bidder 14, they bid in 167 auctions. And what happens is they won 15.6% of the auctions they actually bid in of these 167. Now, if we had if their robot agent was bidding for them, their win rate falls in half. They're only winning 7.2 now. And you say, that's terrible. But think about, this is the profits conditional on winning. They've gone from 292 to 454. So they're winning fewer auctions, but when they win, they're paying less. So they're getting more profits. Now, expected profits are the product of the two. Now, actually, in this case, they went down. Our robot is supposed to be optimal, and it actually makes a little bit less. So I'm gonna have to explain that. But there's other cases where the robot does better. Here, for bidder 11, the robot is doubling the profits. Here, bidder 9, bidder 8 does better, bidder 5. But there's a few cases where they do, this one, it does terrible. Now, how do I explain that? There's a lot of auctions, 163, 227. Here you might say they're one standard deviation. So this bidder is almost optimal. But why is the human doing better, right? Isn't our robot supposed to be it's supposed to be like alpha, alpha 0? And shouldn't it be always beating humans? So what could explain why the humans do better than our robot if I'm claiming they're optimal? Anyone have any, maybe I made a mistake and my dynamic programming is not actually calculating this right. Well, here's my explanation is we assume we are pooling all 533 auctions, but I could show you the value. I should show you the values. These people may be selectively entering certain kinds of auctions. It's like a selection bias. So we're taking average beliefs over 533 auctions. If we recalculate the beliefs on only the 163 auctions this guy participated in, then the robot, we conjecture, we haven't done that yet, we project will actually do better. In other words, there may be some evidence of selective entry into the auctions where their beliefs are better than our average beliefs, and so they do better. Now, so the summary is that if you look in aggregate, though, we are, the total profit for bidders was $79 per bidder per auction, or 600 conditional on winning an auction. In our simulated bidders, they're winning more, 97 per bidder per auction on average, 1,200 or almost twice as much per auction win. They're paying less. They're bidding less because of this overbidding. Now, let me do one final one. This now is let all the bidders be represented. You might say, is this really a counterfactual? We have humans and we're just treating their bids. Wouldn't they have adjusted? So now what we're going to do is all the bidders are robots, but they're bidding at the times the human, all of the people in the auction, they're going to bid at the times the humans wanted them to, but at the values suggested by the robots. And now we don't see the huge reduction because everyone's kind of bidding less. It's bad for the auctioneer. The prices are all going down and they're not winning, much less than they are in the actual auction, but they're just earning a lot more than they would in the real auction. So all these guys in this case are doing better. Now, and then we'll do one more one. The final one is that, and see in this auction here, in this one here too, we assume there's frictions, just a rational inattention. And we said, these are the robots, but they're just as intent, the robots are accounting for the rational inattention of their human masters. Well, let's suppose if you're going to have a robot bid for you in the auction, let's just let the robot go full out. The robot has no inattention. The robot has no bidding frictions. So now we're going to have we're just going to basically say, hey, if you're going to want to collude, let your robots do everything for you. Just put them in as a subroutine and see what happens. Now, what happens then is the robots do not bid early in the auction. All these frictionless robots wait, and then they bid very, very rapidly at the very end of the auction. And when they do that, they are all better off. Okay, so let me show you the final thing. They pay a lot less. This is counterfactual 3. So the average for the auctions winning price with the human bidders is $58.24. That's the actual. The counterfactual is if all these humans, if they were, say they could collude, just have them all write a computer program and let their, they just stick in the values, let their robots bid, they would do way better. Instead of 58, they'd be saving $500 per car per auction. Okay. So when I look at that, I'm saying, well, the managers thought they weren't colluding, it was defeating collusion. And clearly, if they were really super colluders, you would think this is in the strategy, if you believe, perfect rational homo economicus, you would say, well, then they should at least be able to, hire a programmer, and then they all collude by having their robot bidders bid for them, and they decide the values, but we're finding that they're bidding way more than their robots. So we say there's no, from what we see, these guys are not very smart, the bidders. They're not perfectly rational, and they're not colluding, because there's other strategies that could allow them to get lower prices than they're getting. So and then in the end, this is what I showed you yesterday. If you buy that, then here's the 53, way less than this. The best auction is to just go back to a second price sealed bid auction. If they're all bidding rationally there, all they have to do there is just bid truthfully, right? If you think it's worth 8,200, we would just submit a bid, very simple bid, 8,200, and then it would just say you won or you lost. Very easy to program. And what we're hoping is to say, can we convince this manager to try an experiment and say, this is what you're getting now. If you switch to just the second price sealed bid auction, you're gonna win $400 more per car on average. That's a big number when given all the cars they sell. Okay. Thanks for paying attention, and I'm 1 minute over, but have a really good night, and we'll see you tomorrow for the last day. We're going to play more games tomorrow, by the way. More fun and games tomorrow, just to keep you here. And if you guys can straggle through the finish line, we're going to play a leapfrogging game.